So this will be our last day of tediously working through the limit definition to find derivatives. We would have been done yesterday, but somewhere along the way, somebody thought it'd be a good idea to come up with another way to do it. And I've kind of been wondering, like, why? And I've did a little bit of research, and to be honest with you, I have no idea why they have this other way of doing it. But it's called the alternative form of the definition, the limit definition of the derivative. But there's really no benefit to doing it this way as opposed to the other way, from what I can tell. It's just a different way. Huh? Yeah, it's very, very similar. There are some very slight differences, but it's pretty much the same. Now, so why are we going to learn it? Well, because since it does look a little bit different, you guys would be confused if I gave it to you on an exam or something, and they will have that on the exam. So we need to learn both forms. But other than that, I really can't say why we would want to do this. I'll throw one more possibility out there to you, why they might have done it, but even that doesn't quite answer the question very well. But anyway, let's go ahead and start off with a picture like we did before. Draw a graph. So let's go ahead and say that the x-coordinate of this point is C, and let's say the x-coordinate of this point is x. So if this x value is C, then what's the y value that goes with that? Maybe I should tell you the function's name is f. So it's f of c. We'll call it that. All right. So now that we know that, if I call this x value x, this would be f of x. Okay, good. All right. Now, if I wanted you guys to find the average rate of change from here to here, how would you do it? So what's the, let me ask you easier, what's the first thing I write? F of x. Yeah, that's the slope formula, right? y2 minus y1 over x2 minus x1. All right, now, at this point, you don't need to draw on your graph anymore, but what we're going to do is I'm going to, like we did last time, right? Nothing new is happening. I'm going to take this point and I'm going to be dragging it closer and closer to this point. And every time I do, I get a slightly different slope, right? And so what I'm trying to do is I'm getting this point to approach this point, which ends up giving me a tangent line, right? An instantaneous rate of change. So I'm finding the limit of this as what? Good. X approaches C. This is what's known as the alternative form of the limit definition of a derivative. Doesn't it look pretty much the same? I mean, maybe it is. I'm not sure. I don't know if I want to go so far as to say it's easier. Maybe, but it's not less work. I'll tell you that. There's just as much writing involved. But anyway, now you don't need to write this, but I do want to put up there what we learned the past few days, right? I want to bring this back up, and I do want to talk about their differences. But their differences are the only difference is the way it looks. The concepts are exactly the same. Exactly the same. Here's the difference. On this one, we're talking about two y values, right? And this y value happens to be a little bit more than that y value, right? And what we do is we let that little bit more become 0. So they become the same y value, right? In this case over here, we have two y values. And what I do is I let the x values go toward the same point, which causes the y values to go towards the same point. Does that make sense? So here, instead of, this is more like you're letting the distance between the points go to nothing. Here, you're letting the point on the right become the point on the left, but it's really the same concept, right? They're just defining it differently. You know, it's kind of like saying, if I were talking about my sister, if I called her my sister and she calls me her brother, I mean, we're talking about the same relationship here, right? It's just from different perspectives. Same thing. Here you're letting the distance go to 0. Here you're letting x approach c, but they're both accomplishing the same purpose. Okay, so now one difference is this, is that this c represents a constant value. It's not changing. And so a lot of times you're using this one if you want to find the derivative at a specific value, you know. So yesterday's questions went like this. They said find f prime of x using the limit definition. Today's questions are going to look like this. They're going to say find f prime of some number. So we're going to be finding the actual slope at a specific point. Now that's the difference. Now you might think, well, aha, there's the difference. I was kind of thinking that too. But not really, because guess what? If you come up here and you just put c in here, that'll find you the slope at a specific point too. So I literally do not know why they have two forms. I don't know why. Maybe just two different people thought of it. They didn't want to make somebody feel left out, so they just left. I don't know. But we need to know both. That's all I can say. All right. So now that we know that, let's begin. We'll start with something easy. So find f prime of 2 if f of x is equal to 6x minus 9. And I'm going to put in parentheses here using the alternative form. And I'm not going to write out the rest, the alternative form of the limit definition of a derivative. Okay, so first of all, let's do, you do not have to do this, and you don't need to write it, but I just like to review what we learned originally, because that's really what you're going to use all year is the shortcuts, okay? So how would you find f prime of 2? What do? The first thing you do is you find, and then what do you do? So find the derivative, plug in your number, right? So what is f prime of x using the shortcut?
6.
And so what would f prime of 2 be?
6.
So our answer should come out to be 6. Okay? But let's go ahead and do the alternative form of the limit definition of a derivative to see what we can get. So here's the alternative form. We're going to have the limit as x, not delta x, but x, approaches some number. And in this case, it's 2, right? That's the point we're trying to find the derivative at. Over f of x minus f of that same number, which is 2, over x minus 2. Yeah, we'll do that. So this part here, our function is 6x minus 9, right? So if I were to plug in 2, what would I get? 3? No, I think it's positive. 3 is good. I see why I said negative, maybe because of that. But 3 goes there, right? And what is f of x? There's that. So we put the function where the f of x is. We plug in 2 and get an answer and put that where the f of 2 was. And now over here we have x minus 2. Now what would we do? Not yet. Direct substitution won't work because if I do, I get 0 on the bottom. So we can't do that yet. What can we do? I wouldn't say distribute. We will factor, but not yet. What we're going to do is we're going to combine the like terms. What would that give me if I combined my like terms? There we go. And now we're going to factor. Okay? So, what factors out here? 6 does. So if I factor out a 6, what would be inside? Now remember how we couldn't plug 2 in before? Because that was a discontinuity? We can remove that discontinuity. And there it is. And anytime you try to find your limit of a constant, it's just going to be the constant. So, and that's what we knew the derivative was going to be anyway. So there you guys have it. So I think on these ones, factoring will be almost every time. Like I don't think we've had to do that, right, with the other ones we've done so far. So that's a key procedural difference between these two processes. So with this alternative form, factoring comes into play to remove the discontinuity. Let's take a look up here. So first thing you do is you set it up, right? So that's what this was. I just set everything up. Put the number here, here, and here. After that, you plug stuff in. So I replaced f of x with 6x minus 9. I plugged 2 into the f function. I got 3. Then we combined like terms. I'll put CLT for combined like terms. Then we factored, and I'm pretty sure factoring will come into play on almost every problem today, unlike the last one. And then after that, you just evaluate your limit, which usually is just going to be some form of direct substitution. In this case, though, it wasn't. There's nothing to substitute in, so it's just 6. But usually it's going to be some form of direct substitution. So there you go. Very similar to yesterday, just looks a little bit different. That's all. Proceeding? All right, so I'll throw in at you guys here. I like to start with linears just because they're easier. I'd like you guys to find f prime of 8 if f of x is equal to negative 3x minus 1. So we already know the answer is going to be what? Negative 3, but let's go ahead and see if we can get there, just to get used to the process, and then we'll move on to some more challenging here.
Negative 3x minus 1 minus 25.
Close. Minus what?
F of 8.
You could say f of a, but it wasn't at negative 25?
Oh, yeah.
So it looks like this. I think that's where people kind of were getting a little bit confused. Okay? So, you know, you have f of x, right? And then you have f of 8. So it's minus f of 8. F of 8 would be negative 25, right? And so we have these double negatives here, which are going to become positives. Ricardo, what's next, bud? And that gives us positive 24. Okay, how's about Austin? What's next?
Factor out the negative 3.
What would that leave inside the parentheses? And there goes our discontinuity. And your answer is negative 3. Okay? There it is. Questions? Yes?
How do you get the x minus?
On the bottom? That's the setup. Yeah, so like if you look back at this beginning problem, whatever number is here, it's x minus that number. Okay, so now let's move on to some other problems. So you guys have the idea, so I don't think I'm going to do like examples of practice. I'm just going to throw problems at you guys and let you guys drill through them and see if you get the right answers. So let's say I have g of x equals x squared minus 5x plus 9, and I wanted you guys to find g prime of 2. Now the shortcut, what's the derivative of that? And so if I plug in 2, I would get negative 1. So we should end up with negative 1 as our final answer. So see if you guys can use the alternative form of the limit definition of a derivative to find your answer of negative 1 for the derivative. I'm done, but can you tell me what the setup would be?
Yeah, I got x squared minus 5x plus 9.
Uh-huh.
Yeah, parentheses minus 3.
Good. So there's my function. Minus, that's what you get if you plug in 2. And on the bottom we have this, right? Questions about that so far? Okay. Jade. Now what? Find like terms. 9 take away 3 is 6. Okay, good. All right. Brandon's no longer with us. Let's try Juliana. All right, what's on the top?
X minus 3.
X what?
Minus 3. X minus 2.
Okay.
X minus 2.
All right. Remove the discontinuity. Direct sub. Negative 1. Now I noticed that, I don't know about on your papers, but when I call on you guys, you're not like saying like, what do you get? And you guys are saying something like x squared minus 5x plus 6 over x minus 2. You're not saying this to me. Are you writing it?
No, I am.
Because now here's the thing: you wouldn't be wrong necessarily, but remember, I was grading some FRQs from last week's test, and some of you guys did that thing for the piecewise functions. You know, you had to find left and right limits. Didn't very few, but some people did not write those limits on there. They just put they put f of x with a little x with an arrow in it, for instance. You lose it. I know it seems stupid, but that notation is important. So I don't care how you do your homework and stuff, but just be aware if you don't want to develop a bad habit. I know it's kind of a pain in the butt to write it, but just be aware that you want to, if you can, afford the time, then I would encourage you to write it when you can, because you don't want to be developing bad habits of not writing it. All right, let's do another one. How about this? M of x is equal to 3x over x minus 2, and I would like you guys to find m prime of 4. M prime of 4. By the way, what shortcut, if I wanted to use shortcuts, what shortcut rule would I use here? It's quotient rule. What other one would you do? Oh, then it's a product rule. Yeah, you could do that. You could do that. I'm gonna do the shortcut over here. You don't need to write it, but I'm just gonna do it so you guys can see what you should end up with. So low d high minus high below, draw a line, square below. So we should end up with -3/2 as the final answer. All right, guys, let's take a look here. If you're still working and you want to just keep working, you can. I'm going to go through it, though. So I'm going to ask Nathan first. Nathan, what's the setup here? Okay, good. So there's our initial setup, and then we're going to go ahead and start plugging some stuff in. Right? So, Alyssa, I'm going to have you help me plug the stuff in. So, what goes here?
3x over x minus 2.
And what goes here?
Hold on, I didn't write that down. Is it 6?
Yeah, I think it is. All right. Next, I'm going to ask Angelisa. What do I do now? Multiply everything by x minus 2. So this and this cancels, right? So here we've got 3x. And here we're going to distribute a -6. So watch what that does to the signs. You got to watch your signs there. Guys, I don't know if you ever noticed, but I don't usually multiply on the bottom because if you do, you're going to end up obscuring, hiding the factor you want to cancel. So I don't usually end up multiplying on the bottom, but you have to simplify in the top. Ashley's not with us. She's no longer with us. Andy, what's next? Okay, -3x plus 12 then. Okay, Christian, what's next? Factor the top. We could take out a -3. If I do that, I'm left with x minus 4. And then that cancels that. And then we plug in our 4. So you have -3 on the top, and you plug in 4, you got 2 on the bottom. There it is. All right. Good. Yeah, maybe they are a little bit easier. I don't know. There's a lot of letters. But then again, it's kind of hard to compare because we spent, we learned how to do this through those first two, so maybe it makes this one seem easier. I don't know. All right, you guys ready for?
Oh.
What?
Oh, Alex.
No.
That's not nice. That is not nice. That's mean spirited.
Hold on. Oh, no.
Stop it.
Why did
No.
he?
Why?
No, I'm just teasing. I'm just teasing.
The
All right.
next one's gonna be-
This is good though.
the next one's gonna be like-
What? So you're gonna have to watch out for your negatives here,
The
okay?
next one's gonna be Ellen.
I need to find something that will work well because I don't want to get weird fraction answers or something. So no, 0 won't work well. 8 would work.
One.
No, 1 would work. No, 1 wouldn't work.
Oh no, he had negative.
No.
-1.
You guys know what I'm trying to do, right?
Yeah.
10?
5, 2.
Yeah, nice job. Yeah. Because you don't want to get a weird number that gives you a funky square root, right? So if you use 10, you get a nice square root.
Really? Why do we have to do like the long
Oh, yeah,
if that makes sense?
What do you mean?
Never mind. What do you mean?
I mean, I'll show you the shortcut. The
Yeah, but
shortcut would be...
if we can get through the shortcut, it doesn't.
Oh, because answers why the shortcuts work, where they even come from. extra credit videos, which I'll probably give you guys to do over your break if you're interested, is I will prove each of the shortcut rules to you, why they work. Right now we're just doing it on specific functions, but I'm going to show you how you actually use a formula to show, apply this process to a formula to show you a formula for the shortcuts. So
Do we like rationalize in this one?
this is a rationalizing problem. You got to watch out for that minus though, right? That negative, that's going to, because you're going to have a minus and negative, so watch out for that as you're working on it, okay? The negative is probably going to mess you up here. So we have limit as x is approaching 10. Then we have this thing here, minus, and what goes here? Negative 10 over x minus 10, right? So this is, you would get negative 10 by plugging in 10 here, because 3 times 10 is 30, minus 5 is 25, square root of 25 is 5, times negative 2 is negative 10, and of course you have double negatives there, so it's just plus. Now we need to apply the top and the bottom by the conjugate, and that's where people are missing it, okay? So the way the conjugate works, I'm going to rewrite this so it looks a little less ugly. The way the conjugate works is you have two parts. You're going to multiply it by the same two parts, but with a different sign between those two parts. Okay? So I'm multiplying this top by what I just put above it, and then you're also going to put that same thing that I put on the top there on the bottom. I'm going to use a different color just so we don't get confused. So this is the conjugate, the one in orange. So that's what I'm going to multiply to the top and to the bottom. Okay, now on the top, how do you multiply those? Well, usually you'd have to do like a foiling process, right? But with conjugates, there's a shortcut. You don't have to do like a foiling process. You just do this multiplied with this, and this, well, I'm going to include the sign, this multiplied with this. Okay? So see if you can figure out what that would be on the top. I'll give you a second. So Ryan, if I did this times this, what would I have? Very good. And how about these two? There you go. Nice. From there, I think you guys would probably be doing okay. But let's walk through it together because I think we're running out of time here a little bit. So, Dylan, what would I do now?
You would distribute the 4 into 3.
Good. So that's going to give me 12x minus 20 minus 100 over this. And then let me ask Christopher Ignacio, what would I do now? Combine our like terms. Which would give me this. Zach, what would be next? Good. You can take out a 12, right? And now the 10 goes away. Nate, what would I do now?
You plug in half.
Yep. That should take it there. So let's see how that works out for us. The top is 12. The bottom, if I plug in 10 here, what would I get? You would get 5. And that gives me 12 over negative 20, which reduces to negative 3/5. There it is.
Hold on.